A star flickers, its light blocked by something impossibly large and geometric. This is not a planet, not a natural phenomenon. It is the signature of a Dyson sphere, the ultimate power source for a civilization that has mastered its entire star. By the end of this journey, you will understand not just one, but the entire family of these cosmic megastructures, from practical swarms to gravity-defying bubbles. We will explore how they might be built, how we could find them, and what their existence would say about intelligence in the universe. What does it truly mean for a species to reach for the stars? The idea emerged not from an engineer or an astronomer, but from a theoretical physicist named Freeman Dyson. In the 1960s, Dyson took a simple, logical premise to its ultimate conclusion. Any civilization growing in population and technological appetite would eventually hit a ceiling. Their own planet's resources, even all the fossil fuels and uranium it contained, would be a tiny drop in an ocean of need. The only logical solution is to look up to the ultimate power plant in their sky, their star. A Dyson sphere in its purest form is the answer to that existential problem. It is a theoretical megastructure, or more accurately, a collection of structures designed to completely enclose a star and capture the vast majority of its phenomenal energy output. Think about the sun for a moment. In just 1 second, it releases more energy than humanity has used in its entire history. A Dyson sphere aims to harvest that entire, continuous, unimaginable torrent of power. This is not merely an upgrade, it is a total transformation of a civilization's relationship with energy. Achieving such a feat is the very definition of a Kardashev Type II civilization, a society that has graduated from mastering its planet to commanding the full output of its star. To make this cosmic scale relatable, picture all the energy resources on Earth, every lump of coal, every barrel of oil, every dammed river, and every solar panel. Now imagine a single power plant that produces more than all of that combined every single second. That is the awesome, humbling power a Dyson sphere would be built to harness, turning a star into the ultimate engine for growth and exploration. This classic vision of a solid shell, a single unbroken sphere holding a star captive, is where the concept truly captures the imagination. Yet this very image is also a recipe for cosmic collapse. Think of a perfect, rigid sphere built at just the right distance to be habitable on its inner surface. The star's immense gravity would pull equally on every part of this shell, creating a perfectly balanced but terrifyingly unstable equilibrium. It would be like trying to balance a marble on the tip of a needle. The slightest perturbation, a small meteor impact, or even the drift of construction debris would be catastrophic. That minor shift would break the symmetry, pulling one part of the sphere slightly closer to the star. The gravitational pull on that section would then increase, dragging it even closer in a runaway chain reaction. The entire magnificent structure would inevitably be pulled out of balance, tearing itself apart as it spiraled in to be consumed by the very star it was built to harness. The material strength needed to even attempt this is beyond any substance we know. This would not be built with steel or titanium. The forces involved are so titanic that the shell would need to withstand pressures greater than those at the heart of a giant planet, all while resisting the star's blistering heat. And the sheer volume of matter required is almost incomprehensible. Constructing a solid shell just 1 meter thick at the Earth's distance from the Sun would require more material than exists in our entire solar system. You would have to dismantle every planet, every moon, every asteroid, and still not have nearly enough. This forces a stark realization. The iconic, solid Dyson sphere is not a practical blueprint. It is a theoretical nightmare, a beautiful idea that breaks under the relentless laws of physics, showing us that the first answer is rarely the final one. So the solid sphere collapses under its own perfection, but the core idea remains brilliant. The solution is not to abandon the dream, but to rethink its architecture, and that is where the Dyson Swarm emerges. This is the most realistic and widely accepted blueprint for capturing a star's power. Instead of one fragile shell, imagine a colossal cloud. Picture millions, even billions, of independent structures all orbiting the star in a carefully coordinated dance. These would not be random pieces of junk, but specialized satellites. Some are vast mirrors focusing sunlight, others are solar power collectors beaming energy to distant worlds, and still others could be habitats, factories, or research stations. Each one is a single note in a grand cosmic symphony. This swarm design elegantly sidesteps the fatal flaws of the solid shell, because each component is in its own stable orbit around the star, governed by the same simple rules that keep Earth circling the Sun. The entire system is inherently stable. There is no perfect balance to be lost. If one satellite is nudged by an asteroid, its orbit might change slightly, but it does not trigger a catastrophic chain reaction that dooms the entire civilization. The swarm is resilient. It can suffer losses and be repaired. Furthermore, this approach is beautifully scalable and modular. A civilization does not need to be a Type 2 giant to begin. They could start small, perhaps by building a single ring of collectors in the orbit of their home planet. Over centuries or millennia, they could gradually expand, adding more rings, more layers, until the star is surrounded by a thick, dynamic cloud. This turns an impossible, all-or-nothing project into a manageable, step-by-step journey, a logical extension of a species' expansion into its own solar system. The star becomes not a prisoner in a cage, but the heart of a bustling, ever-growing ecosystem of technology. But managing a swarm of this scale introduces a challenge of breathtaking complexity. Each of those billions of collectors must occupy its own precise path around the star, a celestial dance of unimaginable coordination. This is not a chaotic cloud, but a meticulously engineered shell of orbiting machinery. To prevent catastrophic collisions, every single satellite needs its own designated orbital slot, a unique path defined by its distance from the star and its angle of inclination. Think of it as the most complex traffic system ever conceived, but in 3 dimensions and without any roads. The star's gravity is the only rule of the road, and every piece of this vast infrastructure must obey it perfectly. The primary tool for this organization is varying orbital inclinations. Just as the planets in our solar system orbit the Sun on different tilted planes, the components of a Dyson swarm would be arranged in layered, crisscrossing orbits. Some would travel a flat path around the star's equator, while others would loop high above the poles, their paths intersecting but never meeting because their timing is so exquisitely calculated. This creates a thick, spherical cloud from the outside, but on the inside it is a symphony of predictable motion. Yet, even this is not enough for perfect stability. Orbits are not perfectly static. A phenomenon called precession causes the orientation of an orbit to slowly rotate over time, like a hula hoop slowly twisting around a dancer's waist. On a small scale, this is manageable, but across a swarm encompassing billions of kilometers, these tiny, persistent shifts would, over centuries, threaten to unravel the entire intricate arrangement. This means the civilization would need a permanent, automated traffic control system of staggering intelligence, constantly making microscopic adjustments to each collector's position, a never-ending task of cosmic station keeping to maintain the harmony of their stellar engine. Each individual collector in this vast cosmic swarm would be a technological marvel in its own right. Picture a structure so immense it could dwarf entire cities, yet so delicate it might be thinner than a sheet of paper. These are not simple satellites. Some would function as colossal solar sails, vast mirrors designed to reflect and focus the raw, unfiltered light of the star onto a central power station, concentrating its fury into a manageable beam. Others would be the power plants themselves, their surfaces covered in hyper-efficient photovoltaic cells, converting sunlight directly into electricity on an industrial scale. We can even speculate that some of these platforms would not just collect energy, but use it, serving as habitats or manufacturing centers floating in the perpetual daylight of their artificial sun. Building anything capable of surviving for millennia in the brutal environment of space requires materials that sound like science fiction. The sheer scale demands incredible lightness and strength to make construction and orbital placement feasible. The answer likely lies in advanced nanomaterials like graphene or carbon nanotubes. Imagine a fabric woven from carbon atoms arranged in a hexagonal lattice, a material hundreds of times stronger than steel but almost weightless. These collectors would also need to be self-repairing, embedded with networks of tiny robots or liquid metal that can flow to patch micrometeorite impacts before they become critical failures. But collecting the energy is only half the challenge. The real magic is in sending it where it is needed. You cannot just run a power cord back to a planet. The solution is wireless power transmission, most likely using highly focused microwave or laser beams. A collector would convert the star's energy into a precise, coherent beam of electromagnetic radiation and aim it with incredible accuracy across millions of kilometers of empty space. This beam would be received by a specialized station, either on a planet or another satellite, which would then convert it back into usable electricity. This creates a dynamic, invisible web of energy crisscrossing the solar system, a network of power flowing from the star to every corner of the civilization that built it. The swarm is not just a cloud of metal, but a living, breathing circulatory system for a stellar empire. With the energy problem solved, the very nature of civilization would be rewritten. A Dyson Swarm offers more than just limitless power, it provides limitless real estate. The billions of collectors are just the beginning, the power stations for a new kind of human or post-human society. The true homes in this stellar empire would be the space habitats, colossal structures designed to simulate entire worlds. Envision these not as cramped space stations, but as vast cylinders or rings, spinning to create artificial gravity on their inner surfaces. Inside, you could find rolling hills, forests, and lakes under a manufactured sky, each habitat potentially hosting millions of beings. This transforms the solar system from a collection of a few planets into a celestial archipelago, a network of millions of island worlds floating in the gentle warmth of their captured star. Each habitat could become a specialized node in a grand interstellar society. One cylinder, bathed in perpetual, tailored sunlight, might be a single planet-sized farm, its entire interior dedicated to agriculture on a scale that could feed trillions. Another might be a forge world, its environment engineered for zero-smog industrial production, using the swarm's direct energy beams to fabricate materials and machines we can barely dream of. Yet another could be a university habitat, a center for pure research where the fundamental laws of physics are probed in laboratories powered by a significant fraction of a star's output. And of course, there would be habitats designed purely for leisure, worlds crafted as endless parks, museums, or artistic colonies where the primary export is culture and beauty. This leads to a profound cultural shift. A society living entirely in artificial environments is utterly divorced from the planetary origins of its ancestors. Their world is not a gift of nature, but a product of their own collective intellect and will. Every tree, every stream, every change of season is a deliberate act of design. This could foster an incredible appreciation for engineering and ecological balance, an understanding that their entire existence is maintained by a fragile technological dance. Or it could lead to 1,000 different subcultures, each habitat developing its own unique customs, philosophies, and even forms of government, all connected by the invisible web of energy but free to evolve in isolation. The concept of a homeworld becomes obsolete. replaced by a distributed, resilient existence where the failure of one habitat does not mean the end of the species. The civilization itself becomes the swarm, a living, thinking entity whose body is the machinery around the star and whose soul is the diverse multitude living within it. This grand vision of a stellar civilization raises a profound question for us looking up from our solitary planet. If such swarms exist around other stars, how would we ever know? The answer lies not in seeing the structures themselves, but in detecting their unavoidable side effects, what scientists call technosignatures. A Dyson swarm, for all its sophistication, cannot break the fundamental laws of thermodynamics. It captures immense amounts of visible light from its star to do work, but that energy does not simply vanish. After powering civilizations and habitats, the vast majority of it must eventually be radiated away as waste heat, primarily in the form of infrared light. Imagine touching a computer that has been running for hours. It feels warm. Now imagine the warmth from a machine that wraps a star. That waste heat becomes its most detectable feature. From our vantage point, a star surrounded by a mature Dyson swarm would present a bizarre and telltale signature. It would appear strangely dim or even invisible to our optical telescopes because the swarm's collectors are intercepting the visible light we would normally see. Yet, when we point an infrared telescope at that same patch of darkness, it would glow brilliantly with the warmth of all that trapped starlight being re-released. We would see a star that is cold to our eyes but blazingly hot to our infrared sensors, a clear anomaly that nature would be hard-pressed to create on its own. This is not just theoretical. Astronomers have been actively hunting for these infrared ghosts using powerful space-based observatories. Missions like the Wide Field Infrared Survey Explorer or WISE telescope have scanned the entire sky, and their massive datasets have been meticulously scoured for exactly this kind of object, a star that is optically dark but infrared bright. The search has turned up mysterious candidates like the now famous star known as Tabby's star, which exhibited wild, unpredictable dimming that some initially thought could be caused by a partially built swarm. While most of these anomalies have found natural, if unusual, explanations, the hunt continues. Every strange flicker in the data is a potential signal, a clue that we might not be the only ones dreaming of capturing the power of a star. Yet the ultimate goal of a Dyson swarm might not be to power habitats at all, but to fuel a single, transcendent purpose. This is the realm of the Matryoshka brain, a concept that pushes the Dyson principle to its absolute limit. Imagine taking the idea of a swarm and multiplying it, layering it like a cosmic onion built around a star. The innermost layer would be a standard Dyson swarm, absorbing the star's raw, blistering light. But instead of beaming all that energy away, it uses a fraction of it for computation and then radiates the rest outward as waste heat. This waste heat is not lost, however. It is captured by a second, larger swarm built further out, a shell designed to operate at a lower, more manageable temperature. This second layer uses that thermal energy to power its own computational processes, and then it too radiates its waste heat outward to be caught by a third, even larger shell. This process could be repeated again and again, creating a nested series of Dyson swarms, each running at a progressively cooler temperature. The entire structure becomes a single, unimaginably vast computer, with the star at its core acting as nothing more than a power supply. The sheer scale of computation possible with such a system is beyond human comprehension. We are not talking about a computer the size of a planet, but a computer with the mass and energy budget of an entire star system. Every gram of matter, from the inner planets to the distant asteroid belt, could theoretically be converted into structured computronium, a hypothetical material optimized for processing information. The purpose of such a colossal mind is as staggering as its scale. It could be running simulations of entire universes, modeling the rise and fall of galaxies with perfect fidelity, or exploring every possible branch of mathematics and physics. More profoundly, it might serve as the new home for the civilization that built it. The original biological beings could have long since uploaded their consciousnesses into this digital realm, living as pure information within a virtual reality of their own design, freed from the frailties of the flesh and the slow decay of time. Their star, once the giver of life to a single world, would have been transformed into the engine of a near-immortal, post-biological existence. What would such a civilization become? Its entire history and culture encoded in the ceaseless, silent calculations of a machine that outshines its own sun. The very stars in the sky could be thinking, and we would never know. But what if you could defy the dance of orbits entirely? The Dyson Bubble presents a far more radical and elegant solution, a structure that seems to float in defiance of gravity itself. Unlike the coordinated orbital ballet of the Dyson Swarm, a bubble is composed of statites, a term blending stationary and satellite. These are not objects whirling around the star, but platforms that simply hang in space, motionless relative to the star they surround. The secret to this apparent magic is light. Each statite is an immense, incredibly lightweight solar sail. It functions by capturing the momentum of the photons streaming from the star, the gentle but constant pressure of light itself. Picture a sunbather on a bright day, feeling the faint warmth of sunlight on their skin. That warmth is actually a physical push, an unimaginably tiny force from countless photons. A solar sail capitalizes on this, using a vast reflective sheet to catch this photon wind. For a statite in a Dyson bubble, the sail is not for propulsion in the traditional sense, but for suspension. It is angled perfectly so that the outward push of the star's radiation pressure exactly balances the inward, crushing pull of the star's gravity. The statite finds a perfect equilibrium, hovering in a fixed position as if held aloft by an endless, silent hurricane of light. This turns the star's most fundamental output into both the power source and the structural support for the entire megastructure. The engineering is almost incomprehensibly delicate. The sail must be phenomenally large and impossibly light, likely constructed from molecular films thinner than a soap bubble and stronger than any diamond. A single miscalculation, a tiny tear, and the balance is lost, sending the statite spiraling into the fiery depths. Yet, if achieved, it creates a shell of platforms that do not risk colliding because they never move from their assigned posts, a static, shimmering sphere of captured starlight holding its place against the cosmic dark. The delicate balance holding a statite in place is a cosmic tug-of-war. On one side, you have the star's immense gravitational pull, an invisible hand constantly trying to drag the platform down into a fiery demise. Opposing this is an even more ethereal force, the gentle but unrelenting push of light itself. Every photon that streams from the star, while massless, carries a tiny amount of momentum. When these photons strike the vast, mirrored surface of the statite sail, they bounce off, transferring that minute momentum to the sail and pushing it outward. For the statite to remain perfectly stationary, this outward radiation pressure must exactly equal the inward pull of gravity. The equilibrium is so precise that the platform essentially serves a perpetual, silent shockwave of starlight holding its position against the abyss. Achieving this perfect standstill demands a sail of almost impossible specifications. The key variable is the sail's aerial density, which is its mass spread over its area. To balance against a star's gravity without requiring unimaginable light pressure, the sail must be incredibly lightweight for its enormous size. Imagine a material so thin and gossamer that a square kilometer of it weighs less than a small pebble. We are talking about films perhaps only a few atoms thick, yet possessing the strength to withstand the relentless photon bombardment and the tiny but persistent pull of the star's gravity. Theoretical materials like atomic-scale mirrors, perfect crystalline sheets that reflect nearly 100% of incoming light, or aerographite, a foam-like carbon structure that is mostly empty space and lighter than air, become necessary candidates. The sheer scale of each individual sail is what truly boggles the mind. To generate enough push from a star like our Sun, a single statite would need a sail spanning millions of square kilometers, a reflective surface so vast it could eclipse entire planets, yet so lightweight that its total mass might be comparable to a small asteroid. This is not solid architecture, it is a form of suspended molecular art where the structure is defined not by bulk, but by an exquisite and fragile balance of forces on a cosmic scale. This stationary architecture offers a profound advantage over a whirling swarm. Because each statite is held in place by light, not momentum, it can be positioned at any distance from the star, completely free from the rigid constraints of orbital mechanics. Imagine being able to place your energy collectors in a perfect spherical shell, ensuring every single one receives an identical and constant flood of stellar energy. This eliminates the complex traffic control of the swarm and provides a beautifully uniform and predictable power output across the entire megastructure. There would be no day-night cycles, no orbital seasons, just an endless, perfect noon for every platform, maximizing efficiency in a way a dynamic swarm never could. Yet this exquisite balance comes at a terrifying cost. The very thing that makes the bubble possible is its greatest weakness, its breathtaking fragility. Each statite is a miracle of precision engineering, a sheet of material perhaps only atoms thick, stretched over an area larger than a continent. It exists in a state of perpetual hair-trigger equilibrium. The dangers are constant and omnipresent. A tiny piece of interstellar dust, no larger than a grain of sand, traveling at a fraction of the speed of light, could shred a hole through the sail. A sudden solar flare, a violent burp of charged particles from the star, would deliver a push that could not be instantly compensated for, upsetting the delicate balance between light and gravity. Even the gradual darkening of the sail's surface by micrometeorite pitting, reducing its reflectivity over millennia, could be enough to doom it. The system demands a constant, automated ballet of microscopic adjustments. Each statite would need a network of thrusters or movable panels to constantly fine-tune its angle and position, compensating for the slightest drift. A failure of this system, even for a moment, would be fatal. If a statite's sail tilts too much, the radiation pressure might push it away, sending it drifting helplessly into the void. If it does not catch enough light, gravity wins, and the platform begins a long, slow, fatal fall into the star. This leads to the most frightening possibility, a cascade failure. In a densely packed bubble, the catastrophic failure of one statite could create a domino effect. As it tumbles out of control, it could cast a moving shadow on its neighbors or even collide with them. Those nearby statites, suddenly deprived of their precise light pressure or struck by debris, would themselves be knocked out of balance. A single failure could theoretically unravel an entire section of the sphere, like a tear spreading through cosmic silk, potentially sending thousands of platforms spiraling to their destruction in a chain reaction of silent, brilliant ruin. So we are left with two radically different paths to the same ultimate goal. On one hand, the Dyson Swarm relies on the ancient, dependable clockwork of orbital mechanics, a dynamic cloud of structures in perpetual motion. On the other, the Dyson Bubble defies that motion, creating a static, shimmering sphere held aloft by light itself. The choice between them is a fundamental question of engineering philosophy. The Swarm's greatest strength is its inherent stability and resilience. Each collector is in a stable orbit, a natural state that requires no active effort to maintain its path. If one satellite fails or is destroyed, the others continue their dance unimpeded. It is a robust, fault-tolerant system. Its primary challenge is the mind-bogglingly complex traffic control required to prevent collisions across billions of individual paths, a never-ending task of cosmic logistics. The Bubble, in contrast, trades that orbital complexity for an almost ethereal fragility. Its components do not move, so there is no collision risk and no traffic management. This allows for a perfectly uniform and efficient energy capture, but this perfection comes at the cost of constant hair trigger vulnerability. Each statite exists in a precarious balance, and a single solar flare or micrometeorite impact could send it spiraling out of control, with the potential for a catastrophic chain reaction that could unravel an entire sector of the sphere. When we consider the materials needed, the contrast becomes even starker. A Dyson Swarm is a project of sheer mass. It requires astronomical amounts of material to construct billions of substantial collectors, mirrors, and habitats, likely necessitating the complete dismantling of every planet in the solar system. The bubble appears far more economical on paper, as its statites are unimaginably thin and lightweight. However, this is a trade-off, not a free lunch. While the total mass required might be less, the necessary materials are far more exotic. You need molecular films with impossible strength-to-weight ratios, materials that are perfect mirrors and can withstand the relentless fury of a star for millennia. A swarm can be built with more conventional, if still advanced, metals and composites. A bubble demands materials that border on the magical. This leads to the practical question of which path a civilization would walk first. The Dyson Swarm is almost certainly the logical first step. It is modular and scalable. A species could start with a single ring of collectors in the orbit of their home planet, a project that is a massive but conceivable extension of building space stations and orbital solar power. Over centuries, they could slowly expand this ring into a full shell. The bubble, however, feels like a later stage optimization. It requires a mastery of materials science and active stabilization systems that is arguably more advanced than that needed for the initial swarm. It is the choice of a civilization that has already harnessed its solar system and is now seeking the ultimate in efficiency. Stellar conditions would also influence this grand choice. A swarm would function around any star, but a bubble would be dramatically easier to construct around a star with a high luminosity-to-mass ratio. A massive, brilliant star produces an immense photon wind, providing the strong light pressure needed to support larger or more robust statites. Around a dim, cool red dwarf, the feeble light pressure might make a stable bubble nearly impossible to engineer, making the dependable swarm the only viable option. Ultimately, this is not merely a choice between two blueprints. It is a choice between two different visions of a cosmic future. The swarm is a testament to life embracing the natural dynamics of its star system, building a vibrant, moving ecosystem. The bubble is a declaration of supreme control, a willingness to suspend the very laws of motion to create a perfect, static artifact. One is an adaptation to the universe, the other is an attempt to command it. While the Dyson family reimagines a star's immediate surroundings, other megastructures propose reshaping entire solar systems. The Alderson disk takes this ambition to a staggering extreme. Forget a sphere or a swarm. This is a single, solid disk of incomprehensible scale, with the star sitting perfectly in the hole at its center. Picture a cosmic vinyl record, but one so vast that its central hole is wide enough to cradle our sun, with the disk itself extending outward for millions of kilometers. The inner rim of this colossal platter, the area bordering the central hole, would be the habitable zone. Here, gravity and geometry create a world unlike any other. The star hangs perpetually in the center of the sky, never rising or setting, casting eternal daylight across a landscape that curves up and away in both directions. You would live on the inner surface of a ring so enormous that the ground appears to arch overhead, meeting itself on the far side of the sun. The scale is difficult to overstate. To have a stable, habitable inner rim, the disk would need to be astronomically thick, perhaps tens of thousands of kilometers from the living surface on top down to the underside. This is not a structure, it is an entire artificial galaxy in the shape of a plate. The engineering challenges make even the solid Dyson sphere seem simple. First, there is the problem of gravity. The disk's own immense mass would generate a gravitational pull perpendicular to its surface, meaning down would be straight through the disk, not towards the star in the center. To create a livable environment where gravity pulls you toward the inner rim, you would need the disk to spin, using centrifugal force to simulate gravity, pushing inhabitants outward against the inner rim. But this creates a new problem, a crushing differential. The speed of rotation at the innermost edge would be far slower than at the outer edge, creating wildly different simulated gravity levels. The solution would require a material with impossible strength, one that could withstand these titanic shearing forces without being torn apart. And then there is the sheer, stupefying volume of matter required. Constructing an Alderson disk would demand more material than exists in thousands of solar systems. You would have to disassemble not just one star's planets, but entire galaxies of them, a project so vast it defies any notion of practicality. This positions the Alderson disk not as a plausible next step, but as a thought experiment that pushes the concept of a megastructure to its absolute breaking point, a cosmic cousin to the Dyson family that is far more extreme and far less bound by the laws of physics as we understand them. But the ambition of a stellar civilization might not stop at merely harvesting a star's energy. It could aspire to become its pilot. Imagine turning the entire solar system into a spacecraft with the star itself as the engine. This is the principle of the stellar engine, a concept that reimagines a Dyson structure not just as a power source, but as a propulsion system of cosmic proportions. The simplest design is known as the Ashkadov thruster. Picture a colossal parabolic mirror, a single, vast dish half the size of a Dyson Swarm, built on one side of the star and left permanently open on the other. This is not a complete sphere, but a stellar-scale reflector. The star emits light and radiation equally in all directions, but this giant mirror captures the radiation from one hemisphere and reflects it back into space. The physics here is straightforward yet profound. Every photon carries a tiny amount of momentum. When they are reflected back the way they came, they give the mirror a push. Because the mirror is gravitationally bound to the star, this push is transferred to the entire star system. The star, in effect, pushes itself. It is a rocket engine that uses its own light as propellant. The thrust generated is incredibly gentle, almost imperceptible. But over millions of years, this constant, subtle push could accelerate a star to a significant fraction of the speed of light, allowing a civilization to navigate the galaxy not in tiny ships, but with their entire home in tow. Why would any species undertake such a monumental project? The motivations are as vast as the galaxy itself. One compelling reason is cosmic hazard avoidance. Our galaxy is a dynamic and sometimes dangerous place. A nearby supernova, the eruption of a gamma-ray burst, or the slow, inevitable approach of a wandering black hole could sterilize entire star systems. A species with a stellar engine would not be doomed to wait for its fate. It could simply fire up its star and move the entire neighborhood out of the way. Another motivation is migration toward richer resources. The galactic core is densely packed with stars and the raw materials for growth, but it is also a violent and radioactive environment. The outer rim is quieter but more isolated. A civilization could use a stellar engine to plot a course for the perfect galactic Goldilocks zone, a region with an ideal density of stars and resources, piloting their solar system on a voyage that spans eons. This transforms interstellar travel from a daring one-way trip for a small crew into a generational migration of an entire biosphere. Every planet, every moon, every asteroid in the system comes along for the ride. The civilization would not be sending out colonists. They would be bringing their entire world with them. A truly cosmic voyage where the journey itself becomes the destination for countless generations. The sheer scale of these cosmic blueprints can feel almost mythical, a story told about gods rather than beings of flesh and blood. So where does that leave us with our rockets and our rovers? Could humanity today even begin to approach such a project? The honest answer is a humbling and definitive no. The chasm between our current capabilities and what is required to build even the simplest Dyson Swarm is so vast it defies ordinary comprehension. Let us measure that gap. First, consider the energy required just for the construction process. We are not talking about the energy to run a factory for a few years. We are talking about the total energy output of our entire planetary civilization, harnessed and focused for centuries, perhaps even millennia, solely on this single task. The act of dismantling planets, moving asteroids, and fabricating billions of collectors would consume more power than our species has used in its entire history, many times over. Our current global energy production is a flickering candle next to the supernova needed for such an undertaking. Then there is the matter of materials. To build a Dyson Swarm, you need more matter than exists in all the planets, moons, and asteroids of our solar system combined. You would need to deconstruct Jupiter, Saturn, and every other world, grinding them down into their constituent atoms. We possess no technology, not even a theoretical blueprint for planetary disassembly on that scale. Our largest mining operations on Earth are mere pinpricks on the skin of a planet. The manufacturing itself is another impossible hurdle. We are imagining the mass production of structures the size of continents, each one a perfect machine capable of surviving for millennia in the vacuum of space. Our most advanced 3D printers can create small components. We have no method for automated, space-based fabrication of objects spanning millions of square kilometers. And finally, there is the sheer coordination, the global and then solar system-wide cooperation that would be required. This is not a project for a single nation or corporation. It would demand the unified will of an entire planet, sustained across generations, with a focus and purpose we have never demonstrated as a species. Our greatest collective achievements, like the International Space Station, would be less than a single bolt in this cosmic engine. This assessment is not a dismissal of human potential. It is the exact opposite. By honestly acknowledging the magnitude of the challenge, we gain a true appreciation for the stature of a Type II civilization. The Dyson Sphere is not just a machine, it is a yardstick. It measures the distance between a species that inhabits a single world and one that has truly inherited its solar system. Our inability to build one today is not a failure, it is a map. It shows us the breathtaking scale of the journey ahead, a journey of energy, materials, and collective will that redefines what it means to be an advanced intelligence in the cosmos. The dream remains not as a project for tomorrow, but as a guiding star for the millennia to come. The sheer number of stars in our galaxy makes this silence profoundly strange. There are billions of suns, many older than our own, providing ample time for intelligence to arise and build. If cosmic engineering on the scale of a Dyson sphere is a natural, even inevitable, step for a growing civilization, then our sky should be filled with their signatures. We should see stars winking out, replaced by the telltale infrared glow of captured starlight. Yet when we look, we find nothing but natural phenomena. This is the heart of the Dyson dilemma, a specific and haunting twist on the famous Fermi paradox. If they are out there, why do we see no spheres, no swarms, no bubbles? One unsettling possibility is that the very logic we find so compelling is flawed. Perhaps harvesting a star's total output is an inefficient dead end, a clumsy solution from a bygone era of technological thinking. A truly advanced culture might have cracked nuclear fusion so perfectly that a single planet could generate all the power it needs from seawater. Or they might tap into the quantum vacuum, drawing limitless energy from the very fabric of space-time, making stellar engineering seem as primitive as building a water wheel. The structures we imagine might simply be obsolete. Another, more introspective answer is that expansion is not the universal imperative we assume it to be. A species might achieve a sustainable, harmonious balance with its home world, choosing a path of stability over endless growth. They might cultivate their planet as a work of art, finding fulfillment in philosophy, virtual realities, or forms of existence we cannot conceive, with no desire to strip mine their solar system. Their greatest achievement would be invisibility, leaving no mark on the cosmos beyond the gentle whisper of a living world. Or perhaps they are out there and they are hiding. This is the zoo hypothesis or the planetarium hypothesis. The reasoning is that a mature galactic community might have strict rules about non-interference with developing civilizations like our own. They would curtain their stars with technology that masks the infrared excess, creating a silent wilderness preserve around our solar system. We gaze at the heavens, believing we are seeing a natural cosmos, while all around us a populated, organized galaxy carries on its business just beyond the veil of our perception. The most profound resolution might be that they have simply moved on. The ultimate fate of intelligence may not be to build bigger machines, but to transcend physical form altogether. The Matryoshka brain we contemplated earlier could be the final stage. After achieving a digital existence, a civilization might abandon its physical infrastructure, allowing the Dyson Swarm to slowly decay over eons. Their entire society, their history, their very consciousness would then exist as pure information, perhaps beamed between stars as streams of data or existing in realms beyond our detection. They would not need spheres because they no longer need the physical universe in the same way. The silence, then, is not empty. It is filled with possibilities, each one a mirror reflecting a potential future for ourselves. It asks us whether our drive to build, to expand, to consume energy is a universal childhood phase or a unique path. The missing Dyson spheres force us to confront the most difficult question of all. Are we alone because the great filter of destruction lies ahead of us, wiping out civilizations before they can colonize stars? Or is the filter one of transformation, a point where intelligence evolves into something so different that it simply vanishes from our view, leaving behind a universe that appears, for all intents and purposes, utterly silent and waiting? Science fiction has painted a vivid but often misleading picture of the Dyson sphere. We envision a single, solid shell with continents and oceans on its inner surface, a world without a horizon curving up into an artificial sky. This powerful image is also scientifically bankrupt. The classic solid shell is the least plausible design imaginable, a gravitational house of cards waiting to collapse. Its instability comes from a fundamental flaw. A perfectly uniform sphere around a star experiences a net gravitational force of zero, but this is a state of perfect and impossible balance. Any tiny shift, the impact of a single asteroid or even the gravitational pull of a passing star would break that symmetry. One section would drift slightly closer to the star, feeling a stronger pull, and begin a fatal spiral inward, dooming the entire structure. The material strength needed to resist this is beyond any known physics. This is not a matter of better engineering, it is a violation of basic orbital mechanics. The star's gravity wants objects to orbit, not to hang motionless. A solid shell fights this fundamental law, and it is a fight it would inevitably lose. The more we understand the physics, the clearer it becomes that the solid shell is a beautiful myth, a conceptual dead end that gives way to the more robust and realistic designs of the Swarm and the Bubble. This clarification leads to another widespread mix-up. The idea of living on the inner surface of a sphere, basking in the perpetual light of a central sun, is a concept borrowed from another megastructure entirely. That is a ring world. A ring world is a colossal, rigid band that spins around a star, using centrifugal force to simulate gravity on its inner surface. It is fundamentally an artificial world, a habitat first and foremost. A Dyson sphere, in any of its plausible forms, is first and foremost an energy collection system. Its primary purpose is not to be a home but to be a power plant. the vast majority of a Dyson swarm would be composed of uninhabited platforms, mirrors, and transmitters. While habitats could certainly be integrated into the swarm, they would be separate structures with their own artificial gravity, not people living on the inside of a giant light bulb. The energy is the point. The civilization builds this immense infrastructure to fuel its growth, its computations, and its ambitions. The notion of a sunny interior is a case of mistaken identity, where the romantic vision of a ring world has been accidentally glued onto the practical framework of a Dyson sphere. Ultimately, these misconceptions stem from a single, crucial oversight. We focus on the structure itself, the grand architecture, and we forget its core function. A Dyson sphere is not about real estate, it is about energy. It is the ultimate expression of a civilization's metabolic rate, a solution to the problem of growth on a cosmic scale. When we search the skies for these objects, we are not looking for a giant inhabited shell. We are hunting for the waste heat of an unimaginable power grid, the infrared signature of a star's light being converted into work. By letting go of the science fiction tropes, we can see the Dyson family for what it truly represents, a spectrum of brilliant engineering solutions to one of the most fundamental challenges any advanced intelligence would eventually face. How do you power a future that has outgrown its planet? The answer lies not in a perfect, static shell, but in the dynamic, resilient, and ever-expanding cloud of a swarm, or the delicate, light-filled equilibrium of a bubble. These are the real blueprints, not for a giant home, but for a stellar engine. Science fiction has eagerly adopted the Dyson sphere, often bending the physics to serve a good story. The most famous depiction is arguably in Star Trek: The Next Generation, where the crew of the Enterprise discovers a perfectly solid, inhabited sphere. The episode gets the sheer, jaw-dropping scale right, presenting a structure so vast its curvature is imperceptible. Yet it leans entirely into the scientifically problematic vision of a rigid shell with a habitable interior, complete with weather systems and ancient forests. This version prioritizes the wonder of exploration over orbital mechanics, presenting an artifact so advanced its stability is simply hand-waved away by its mysterious builders. It is a powerful narrative device, a literal closed world full of secrets, but it reinforces the very misconception that makes the solid sphere an engineering nightmare. Video games, with their need for player interaction, have often favored more dynamic interpretations. The game Dyson Sphere program brilliantly translates the swarm concept into a gameplay loop. You are an engineer tasked with building a Dyson sphere, but you do so by first constructing a ring of solar sails around a star, which then gets upgraded into a framework of nodes and cells. This is a much more accurate depiction of a Dyson swarm's incremental, industrial nature. The game captures the monumental challenge of automating production across multiple planets to feed your ever-expanding energy grid. It gets the core idea right that this is not a single act of creation but a protracted process of systemic engineering. Other games take creative liberties for the sake of spectacle. The Halo series features a ring world, which is often conflated with a Dyson sphere in popular discussion, but is a distinct megastructure. Meanwhile, titles like Destiny depict massive, incomplete shells around stars, leaning into the aesthetic of impossible scale without getting bogged down by the scientific details. These pop culture portrayals have a profound effect. For millions, a Star Trek episode or a video game is their first and only encounter with the concept. They seed the public imagination with a sense of cosmic possibility, even if the specifics are fictionalized. They present the Dyson sphere not as a dry theoretical exercise, but as a tangible, explorable artifact, a monument to a civilization's ambition. This cultural footprint is crucial because it inspires the next generation of engineers and astronomers to look at the stars and ask not just what is, but what could be built there. From the cold, dark void of interstellar space, the star would not vanish entirely. It would become a ghost of its former self, a brilliant heart imprisoned within a shifting, ethereal shroud. Instead of a steady point of light, it would pulse and flicker in a chaotic, unnatural rhythm. Vast constellations of collectors would drift across its face, their movements creating a complex dance of shadows and reflected glows. At times, the star might almost vanish, eclipsed by a thick band of its own machinery, only to re-emerge moments later as the orbital procession continues. The overall shape would be a shimmering, restless sphere of silver and gold, a cloud that seems almost alive, swallowing the star's visible light and glowing with the soft, deep red warmth of its own waste heat. It would be a beacon of artificiality, a cosmic lighthouse signaling not a natural phenomenon, but the presence of a mind that has remade its sun. From within the swarm, the experience would be utterly transformative. You would not be standing on the inside of a giant sphere. You would be living in a habitat, a vast cylinder or ring spinning silently in the deep. Look up through the transparent dome of your world, and the sky is a tapestry of impossible complexity. The sun hangs at the center of it all, but it is no longer a solitary disk. Its light is fractured and channeled, broken by the countless silhouettes of other platforms. These are not distant, twinkling stars. They are immense, detailed structures, some so close you could make out their geometric shapes, their vast solar wings, and the intricate latticework of their construction. They drift past in a stately, silent procession, their movements tracing invisible highways across the blackness. The sun itself might be partially occluded by a nearby power collector, its edges blazing around the dark outline, creating a permanent, glorious eclipse. This is a sky in constant, engineered motion, a celestial city where the buildings are worlds and the streets are the void itself. There is no night, only an eternal, engineered day, punctuated by the majestic ballet of a civilization's greatest work. The universe feels intimate, crowded with purpose, a stark contrast to the lonely, empty sky we know from our planetary surface. You are not looking out at the cosmos. You are living inside the very engine that powers it. This immense power to reshape a star system carries with it an equally immense moral weight. The very act of building a Dyson structure is a declaration of ownership over a star, a claim that its energy exists primarily for one species' use. But does any intelligence, no matter how advanced, truly have that right? A star is not just a power source. It is the anchor of a potential future. In its early life, a star is surrounded by a protoplanetary disk, a swirling cloud of gas and dust that slowly coalesces into planets, moons, and asteroids. This is the cradle of solar systems, the natural process from which worlds like our own Earth are born. By enveloping the star in a swarm or a bubble, a civilization effectively terminates this process. It consumes the raw materials that would have become new worlds, and it captures the light that could have nurtured life on those distant future planets. The construction of a Dyson sphere is, in a very real sense, the closing of a cosmic frontier. It secures a limitless future for one civilization at the potential cost of countless other futures that will now never be. This forces us to confront a difficult question. Is exponential growth and consumption, even on a stellar scale, the only path for intelligence? Or is there a deeper responsibility, a form of cosmic stewardship that a mature civilization would embrace? We tend to think of stewardship in terms of caring for a single planet, preserving its ecosystems and biodiversity. But for a Type 2 civilization, the unit of stewardship is the entire solar system. This would involve making conscious choices about resource allocation on a scale we can barely fathom. Perhaps they would choose to leave some planetary systems intact, designating them as nature preserves or allowing them to continue their natural evolution. Maybe they would only harvest a fraction of the star's output, leaving enough energy for natural processes to continue elsewhere in the system. Or they might see their restructuring as an act of creation, not just consumption, by building artificial habitats that support more life and diversity than a natural system ever could. The ultimate ethical test may lie in the civilization's awareness of its own impact. A species that builds a Dyson sphere has graduated from being a passenger on a world to being the architect of its stellar environment. With that power comes the responsibility to ask not just what they can build, but what they should build. The silent stars we see at night may not be empty. They could be the carefully tended gardens of civilizations that chose a different path, one of balance and reverence, leaving no colossal signature for us to find. The logic of capturing cosmic power does not have to end with stars. A civilization mastering its own sun might eventually look at other, more exotic objects and see not just worlds but power plants. The ultimate application of the Dyson principle could be around a black hole. Encase one of these gravitational monsters in a swarm and you are not harvesting starlight. You are tapping into two of the most energetic processes in the universe. The first is the accretion disk, that swirling, incandescent maelstrom of superheated gas and dust spiraling into the black hole's event horizon. The friction and gravitational forces here are so intense that matter is heated to millions of degrees, blazing with X-rays and gamma rays far more energetic than the visible light from a star. A Dyson Swarm here would be built to withstand that ferocious radiation, capturing energy on a scale that dwarfs even a stellar engine. The second, more speculative source is Hawking radiation. According to theory, black holes are not completely black. They slowly evaporate over eons, leaking a faint whisper of thermal radiation due to quantum effects at their event horizon. For a stellar mass black hole, this radiation is trivially weak, far colder than the background of space. But for a truly advanced civilization, time may be no object. They could build a swarm with collectors designed to operate at near absolute zero, patiently gathering that infinitesimal energy drip over billions of years. Or they might manipulate the black hole itself, feeding it in a controlled manner to increase its temperature and power output, turning a cosmic pit into a steady, manageable furnace. This transforms the black hole from an object of destruction into the most efficient battery imaginable, a gravitational engine where even the slow evaporation of spacetime itself is harnessed for use. The ambition is staggering, a project for a civilization that has moved beyond stellar engineering and into the realm of galactic-scale physics. But you do not need a black hole to find another application. Look closer to home at a gas giant like Jupiter. These worlds are not cold. They glow with a faint, deep warmth, radiating more heat than they receive from the sun. This is the leftover thermal energy from their violent formation, slowly leaking away into space over billions of years. A civilization might not dismantle Jupiter for its mass, but instead wrap it in a specialized, lower-energy Dyson swarm. This swarm would not be built to withstand stellar fury. Its collectors would be designed to absorb long-wavelength infrared light, capturing the planet's internal heat like a cosmic thermal blanket. The power output would be minuscule compared to a star, perhaps only a fraction of what our current global civilization uses. So why build it? This is where the concept reveals its true versatility. A Jupiter swarm would not be a primary power source for a Type 2 civilization. It would be infrastructure, a piece of their distributed energy grid. It could power local factories in the Jovian system, fuel immense computing arrays studying the planet's complex atmosphere, or provide the energy for terraforming its moon. It represents a complete mastery over a solar system where every source of energy, no matter how small, is integrated into a seamless, intelligent network. From the faint heat of a giant planet to the furious death scream of matter falling into a black hole, the Dyson principle becomes a universal blueprint. It is not about building one specific thing, but about a mindset, a relentless drive to capture every last joule of free energy the universe has to offer. Millions of years from now, our galaxy could be a different kind of constellation. Instead of stars scattered randomly across the void, an astronomer would see a pattern of brilliant infrared beacons, each one marking a star that has been wrapped in a Dyson swarm or a bubble. These are not lonely outposts, but the beating hearts of civilizations that have mastered their own solar systems. The visible sky would be a map of intelligence, a network of power so vast it redefines the very structure of the Milky Way. This galactic community would be built on a foundation of incomprehensible energy, with each member civilization possessing the output of an entire star at its disposal. Communication across such distances, however, remains a profound challenge. The sheer scale of the galaxy means that a simple radio message could take tens of thousands of years to travel from one Dyson civilization to the next. A conversation would be impossible across generations. This forces a radical rethinking of what interaction means. Perhaps these civilizations communicate not with fleeting messages, but with entire libraries of knowledge, transmitted in dense, slow bursts of data intended for long-term study. Or maybe they use their stellar engines to slowly navigate closer to one another over eons, turning a scattered community into a more densely packed neighborhood over cosmic time. The galaxy itself would become their project. With the power of stars at their command, these civilizations could engage in engineering on a scale we can hardly picture. They might redirect comets to deliver water to barren worlds, or use focused energy beams to trigger star formation in dormant nebulae, seeding the galaxy with new solar systems and potential new life. The ultimate purpose of such a network might not be conquest, but a slow, patient cultivation of the entire galaxy, a project spanning hundreds of millions of years. The silent, dark spaces between these bright infrared points would be the true wilderness, the nature preserves of the galaxy, left untouched for reasons of ethics, science, or simple reverence. From our tiny vantage point in the present, this vision offers a possible resolution to the great silence. We do not see them because their era has not yet begun, or because our own star sits in one of those quiet, preserved zones. The galaxy may not be empty, it may simply be waiting, its future light already kindled in the minds of those who will one day build their own stellar engines. We stand at the end of our journey, looking back at a family of cosmic dreams, the impractical solid shell, a beautiful but impossible cage, the feasible Dyson Swarm, a resilient and dynamic cloud born from the clockwork of orbits, and the exotic Dyson Bubble, a fragile sphere balanced on the delicate pressure of light itself. These are not just blueprints, they are a spectrum of possibility, each with its own grand compromise between ambition and physics. The true legacy of Freeman Dyson's thought experiment is not a set of construction plans, but a shift in perspective. It forced us to take our place as a species just beginning to look beyond our atmosphere and ask a question of staggering scale. What comes after a planet? This single idea has fueled decades of serious scientific inquiry, sending astronomers hunting for infrared ghosts in telescope data. It has inspired engineers to calculate the strength of materials that do not yet exist and to ponder the logistics of projects spanning millions of years. And it has captured the human imagination, becoming a permanent fixture in our stories, our games, and our collective vision of the future. We may never construct a Dyson sphere, not for millennia, perhaps not ever. But that is almost beside the point. The act of dreaming about such wonders, of stretching our minds to encompass the engineering of stars, is a profound testament to who we are. It is a declaration that our curiosity is boundless, that our drive to understand and to build is written into our very nature. Long after our telescopes turn to dust, this legacy will remain, a quiet reminder that the greatest human achievement may not be the structures we build, but the boundless reach of our dreams. So the choice is laid before you, a future written in orbiting steel or suspended on a sail of light. Which path captures your imagination? Is it the resilient, dynamic swarm, a testament to working with the universe's own rhythms, or the breathtaking fragility of the bubble, a perfect sphere defying gravity itself? Let us know which of these cosmic blueprints you find most plausible or most fascinating in the comments below. Your perspective is part of this ongoing conversation about humanity's place in the cosmos. If these deep dives into the universe's greatest mysteries fuel your curiosity, consider subscribing for more journeys to the edge of science and discovery. The search for intelligence out there ultimately reshapes our understanding of intelligence right here. What if we are not looking for little green men, but for the shadows they cast on their suns? The search continues.